Well, hello everyone. Welcome back to Adrian's Digital Basement 2. On today's video, I'm following up from last week's video where I underclocked and overclocked an NES. And I did that by swapping the CPU from the NTSC console onto the Dendy console. Dendy being a PAL variant made by the clone manufacturers that should run at a clock speed that is more compatible with NTSC consoles while running it in 50 Hz PAL mode. Putting the NTSC CPU that's from this board onto my Dendy console, which is my front loader NES, then it actually overclocks this CPU to around 2.2 megahertz, and it totally works. Of course, the problem is, while that is in the Dendy console with the Dendy PPU and the Dendy 26 megahertz crystal, the entire system is running at 50 hertz, which means all the NTSC software that I'm used to runs, well, at 50 hertz, 50 frames per second. So it all just runs a lot slower. So on today's video, what I want to do is I want to try to run the CPU at an asynchronous and arbitrary clock compared to the master clock that's running the entire console. On NTSC NESs, and these are the original Rico PPU and CPU, the master clock is 21.47727 megahertz. That gets divided by 12 inside the CPU to result in around 1.78 megahertz for the 6502 core that's in here. And then the PPU itself is, generating all the 60 hertz NTSC style graphics based on the master clock, including the color bursts and stuff like that. So you cannot change the crystal oscillator. The master clock needs to be this if you're going to run an NTSC PPU. And if you're going to run a PAL or a Dendy PPU, then you have to use the 26 point whatever PAL crystal oscillator that goes with that PPU. It's the processor that normally takes the clock generated by the master clock and then internally divides it by 12 or 15 in the case of the Dendy CPU, and then that's what gets you that internal clock speed. So what I intend to do in this video is lift the clock input pin to the CPU and then just drive it arbitrarily with my little arbitrary signal generator. This thing can go up to 30 megahertz, which is plenty for our purposes. I've actually started it running at 21.477270 megahertz, which happens to be exactly what this runs at. And I think the first test we want to do here is I need to see if this can even work. Obviously, if I'm using the generator versus the master clock, these two things won't be PLL locked anymore, which means theoretically, because they're no longer phase locked, that could keep it from working. Even though I have this set up at the same exact frequency as the master clock, it's not exactly right. Like there's slight drift. These are devices here that aren't synchronized. So I actually have really no idea if this is even going to work, even trying just to run at the stock clock speed like we are here. So I've lifted up pin 29, which happens to be the clock input to the CPU. And if I try to turn this on right now, well, it's not going to work at all. So what I'm going to need to do is I need to then feed the output of this into the clock input of the CPU, and then we should power this thing up and see if it's going to work. To facilitate that, I'm just going to use some clip leads. So this is the clock output from the generator, and I'll just clip that right onto there, but I've got to also clip on a ground lead. And to do that more easily, what I'm going to do is I'm going to solder this red wire, it just happens to be what I have, onto the ground lead of the CPU. That way the clock output of this is fed directly into the CPU. And then for the signal itself, I'm actually going to use this wire here because it just has a little clip on the end. It's a little easier to use. And there we go. All right, so as it is, this thing is turned off. So there's no clock going into the CPU. So if we turn this on, yeah, we're going to get absolutely nothing. That's just the PPU generating its video signal based on the master clock that's on here. So what I can do is we can turn this on, and then I can turn that on. We can hit reset. And there we go. The system is working. So we'll just run a game here. I'll turn the sound down so we don't have to hear it. That interference pattern, by the way, that's just this crappy Famiclone board. It just, it does that. I talked about that in the last video, what we're actually seeing there. Okay, so asynchronous clock input into the CPU, no problem whatsoever. There's a little bit of weird lines that we have going on here. So I guess my little connection setup here is not the best. But that is, well, doesn't really seem to be causing a problem. So cool. Also, I just realized that this thing is dual channel. So theoretically, I could output both the master clock and the other clock, the CPU clock, and alter them separately if that somehow matters. But I don't think that really matters because we're getting perfectly good video right now. So we'll turn the CPU clock off, and that, of course, crashes the console. Turn off the console. Let's switch over to my clone EverDrive, because what I want to do is I want to load up 240p test suite, because that will actually show us the exact clock speed that we're running at. So again, we'll do the same sequence, turn it on, hit reset, should boot up. Yep. And I think 240p test suite was the last thing I was using. No, it was actually Contra Force. Okay. Now the thing about Contra Force, the reason why I have this up is this is a great game for testing lag. I was talking about using Super Mario Bros. 2 for lag testing, but this game is ultra laggy. Now what I didn't do in the last video is I did not test this game on the Dendy console without the overclock. So just the stock clock speed of 1.777 megahertz or whatever it runs at. Now, that's the same clock speed as the NTSC system, but the thing is, the Dendy system actually adds about 50 extra scan lines to every single frame because it's running at 50 hertz versus 60. That gives games more time to do the calculations for the next frame. So this game on the Dendy console is way less laggy than it is on NTSC. NTSC just, it's lag fest constantly. On Dendy, it's less severe. It still lags though. But what I did do in the last video is I played this game with the overclock and I couldn't detect any lag. So let's just run this now. We're using the stock clock speed, right? We're at 21.4477270 megahertz. And let's see what this runs like here. And I'll turn up the sound a little bit. Okay. So far, oh, it's already lagging. I just felt some lag right there. Yeah, it's lagging already pretty badly. Like the game, when it's not lagging, it feels relatively good at, like, it's smooth. But when it lags, which is like, the guy moves so slowly. Like right now, okay, now it's not lagging. So he's like moving at a normal pace. But as soon as you get a couple characters on screen, like his maximum running speed is like half as fast. So anyways, okay, let me just play a little bit more of this just so I can get a feel for it, and then we'll try overclocking. Oops, it's bad. All right, let's stop the CPU, and let's try turning up the frequency. Okay, so let's do a little bit of calculations to figure out what's going on. That's our current clock speed that's coming out of this, and remember I mentioned the CPU is dividing that by 12, so we're getting 1.789 megahertz. That's what the NES CPU is currently running at. If I run this at 30 megahertz, that's the maximum speed that it supports, obviously we're going to get 2.5 megahertz. That might be a bit of a greedy overclock, although that's a substantial performance improvement over the 1.78 megahertz. I know for a fact this thing can run at like 2.2 megahertz or so, which is roughly 26.6 megahertz, which is the PAL oscillator. And of course we divide that by 12, and that gives us that 2.21. I know it was working at that rate when I had the CPU swapped around. So this CPU in the other console. So let's try running it at that speed. And let's see if, well, let's see how well it works. So 26.6, I mean, it doesn't even matter to be that specific. So there we go, 26.6 megahertz should give us 2.21 megahertz. And we can verify that by going to 240p test suite and looking at the CPU speed. Now, one caveat I'll have to add, and I mentioned this in the last video, is changing the clock input to the CPU will affect the sound, as the CPU is what generates all the sound on the NES. It should not affect how quickly the music is playing, the tempo of the music, because that should be tied to the non-maskable interrupt, which is tied to VSync. So 60 hertz in the case of this NES. That's not changing by what we're doing here. But I think the tonality or the frequency of some of the notes and things, that will change because that's generated based on the clocks inside the CPU. I guess we'll find out shortly. All right, here we go. Let's turn this on. So the sequence, by the way, is this is off. I turn the console on, I turn this on, the output, and then I hit a reset button, and that brings the CPU up. So we're currently running. Let's go to 240p test suite. Let's see what we got. And yep, down in the bottom right corner, it would normally say NTSC or Dendy or PAL. It doesn't say anything there because it doesn't really know what's going on at the moment, because there we go, 2.217 megahertz. And we are running at an NTSC, of course, so the frame rate is correct. And the interesting thing is the cycles per line. That is how many CPU cycles are happening during each scan line. The stock NTSC console and the Dendy console running in its stock configuration gives about 113.7 cycles of the CPU per scan line. We're getting 140.8, so this is our overclock that is somewhat substantial. Now, when I had this CPU inside the Dendy console, I think the frequency of the oscillator was a little bit faster. It was like 26.6 something. and it was running at 142.1 cycles per scan line. So that was slightly faster than we're getting now. But the other trick is with Dendy is because there are more scan lines and it's running at 50 hertz, it actually gives the CPU even more time per frame because non-maskable interrupts only firing every 50 hertz or whatever it was, 50.01 hertz versus this 60.1 hertz that we're getting here on NTSC. So even though the cycles per line is similar between the overclock we were doing in the last video, it's not exactly the same because there are less scan lines per frame the CPU can calculate the next frame with. There are actually exactly 50 less scan lines, and if we multiply the number of cycles by scan lines, there are 7,040 less cycles per frame available on this setup right now than we had on the Dendy CPU. So stuff that didn't lag at all on Dendy might lag a little bit on here, but I mean, we're overclocked though, that's the thing. And look, it's still running. I mean, let's just go through a few things here. Let's look at hill zone scroll test. Okay, so this is one thing that always seems to screw up when you're overclocking, and it's the split that's happening there. See that little foamy part under the waterfall? I don't think that should be scrolling from side to side. I can speed this up a little bit if I push up arrow. And I think this is using CPU cycle counting, and of course we have more cycles than it expected, so that alters it. Now, one thing that is I'm kind of curious about is, can I change the CPU speed while everything's running? Oh, I can. Oh, wow, okay. Yep, I'm slowing down the CPU right now, and it doesn't seem to crash the console. Let's see if the CPU speed is in real time. Oh, it is. So I can alter the CPU speed while it's running, and it, it just works. Okay. Well, I guess I could do a couple things. We can see how fast we can go. So this is back to where we were running right there, 140.8. Can I go faster? Yeah. I mean, I'm getting greedy here, aren't I? But the master clock right now, or the clock that's going into the CPU, by the way, is 25.5. So we're approaching the limit of my little generator. It can only go up to 30 megahertz. I assume it's going to crash eventually, but so far it's not. Okay. Well, there. I'll stop here at 2.4 megahertz, 152.4 cycles per scan line. Let's just see. Let's just see exactly what that does. I think if we go to the hill zone, that split for the waterfall will look even more screwy. Yep, there it is. So any game that's using this kind of cycle counting is going to be problematic. But I don't think a lot of games use this. Well, because the later versions of the mappers handle this in hardware. I think they're basing, I don't actually know how they work. I don't know if they're using the clock frequency to do it, or maybe they're using the master clock to do it or something. But that's like the HUD splits and things like that when you have Super Mario Brothers 3. We'll test that. And I could just change the clock speed in real time and we can fool around and see what happens. So here's what I'm kind of curious. Here's 500 hertz. Does this change if I change this frequency? Yes, it does. Do you hear that? So this is kind of what I was talking about. It's going to affect the sound, and I don't know how it's going to actually sound in games affected, but I think we can play this crowd thing. So, all right, so that gives you a little idea. It was changing the music as it was playing. All right, well, let's try a game and let's see what happens, right? Let's start with Super Mario Brothers because we all know how this sounds. And we're running at 28.8 megahertz. Let me just calculate the exact clock speed that is. 28.8 divided by 12, that's 2.4 megahertz. Yeah, so we're at the 2.4 megahertz right now. Okay, so I wasn't detecting any issues whatsoever. I mean, my playing was terrible because I'm playing through OBS. I know I've said that a million times, but the game itself was working fine. Zero issues whatsoever. Other than, of course, the music was way weird and out of pitch, but the tempo was correct. And this just sounds so weird as well right here. Also, I'm noticing that we're getting some sparkles. And this is glitching out. Okay. What I'm going to do here is we're going to turn the system off, and I'm going to switch over to this multi-cart, because I'm wondering if the EverDrive is more sensitive to clock speed than this multi-cart. I did all the testing in the last video using this 154N1 kind of remix multi-cart that I've just had kicking around for the longest time. So turn it on. Let's get this going, and let's try Super Mario Brothers 2 in this cartridge. See if this is less affected and sparkly. I don't see any sparkles here. Okay, so we're at 28.8 megahertz on the master clock, or clock going to the CPU, and look, it's all totally glitching and going wild. But 26.6, 26.5? That's still glitching a little bit. Oh yeah, still a little glitchy. Interesting that it's doing this. All right, I'm going to put it down to 28.0 megahertz on the master clock. You know, the glitching obviously can happen for a number of different reasons, right? It can happen because the CPU is talking to the PPU, but it's talking to it at a much higher rate. Like the chip select and all that stuff is happening more quickly than it normally would. And that can cause issues. Even if we could run internally the CPU at, say, 4 megahertz, that's just going to be way too fast for it talking to the slow ROMs and the cartridges and also the PPU itself. So you have to do this within reason. But yeah, like whatever we're at now, what is this, 28.0? Let's do a calculation to find out what this is. Okay, we're running at 2.33 megahertz right now. Still faster than we were running the overclock in the last video. All right, let's see. This was my test when I threw the Shy Guy off. Yeah, loads of lag and zero lag there. Zero freaking lag. I'm just amazed this works. I'm really amazed. Now, of course, I can go the other way and I can slow this down. So we're at 28.0 megahertz, right? Okay, we're now at 18 megahertz for the clock. Okay, now we're at 14 megahertz. That means the CPU is running at 1.16 megahertz, and we should have like massive lag. And look, it's glitching out as well. Oh, and it's really, really laggy right now. Like, it's unplayably laggy. Game's still fine, except for the weird hiccuping it's doing. How about Super Mario Brothers 3? Let's see if this works without glitching, other than the sound being weird. So far, everything works perfectly here. The only thing that's weird is the transition there between the actual play field and then the HUD at the bottom. Normally, the glitch is way over on the left side, just right above the HUD. And now it's way over on the right side. And that will obviously change if I move the clock speed. See, I can affect where that's actually rendering. So at 23 megahertz, the glitch is actually happening inside the horizontal blanking interval. So you don't see it at all. That's funny. Of course, 27 seems like a good sweet spot. Not so much for that particular glitch, but everything seems to work properly. Like there's no problems with the game so far at 27 megahertz. And yet we get a great speed up where the lag has been removed. Now let's see what Contra Force is going to do. We have a 26% speed up for the CPU core itself running at 27 megahertz going into the CPU. So let's see if this is now lag free. Oops, I'm playing terribly, but yeah, so far it's zero lag. Wow, so this is how the game is supposed to be? This is unbelievably different. It's fast. Amazing. Oh, a little bit of lag right there. game is definitely hard. All right, well, what have I learned playing this game? Well, first off, even at 27 megahertz, there's still some lag. It's a lot less. I cranked it all the way up to 30 megahertz going into the CPU, which resulted in 2.5 megahertz on the CPU, and now it's actually not really too laggy. It still lags a little bit here and there, and that's, of course, with NTSC without all those extra Dendy scan lines, but this is definitely the way this game is supposed to be played. I'll just run through a quick level here and we'll just show you that it is not slowing down at all. I mean, okay, slow down a little bit right there. It's night and day how fast this game feels when it's not all horrible and lagging out. Oh boy, it's hard. I'm not good at it, that's for sure. So yeah, here we go, and we got our forklift, and you get stuck over on the right side. You kind of have to go back to put yourself more in the center again, otherwise it becomes extra hard. But yeah, generally this game's running at 60 frames per second now. The game that can never run at 60 frames per second. And obviously, I'm maxing out my frequency generator, and there's no issues with the CPU running at this speed. So I guess it's like your mileage may vary depending on game to game, and probably even cartridge to cartridge. Yeah, I'm going to get smushed there. I'm actually not sure how to even get through that part, but your mileage may vary from game to game whether it can work at this accelerated clock speed, but definitely Contra Force, it works perfectly fine. Now, oddly enough, here in the menu for the 154-in-1, this is glitching out. I can't even see which game I'm selecting right now. Let me just reset one more time. But yeah, it's obviously not working properly at this speed, so let's turn this down a little bit. Oh, there the arrow appeared. So yeah, I think it's going to really vary from game to game. And that's why if we had something that like an FPGA you could change on the fly, that would be a good solution. Of course, none of this fixes the audio. That is completely messed up. But here we are running at 28 megahertz, and let's see if Simon's Quest works. Yeah, no issues. Okay. I mean, the audio is weird. Watch, I'll change the audio while we're listening to the music. All right, so we're at 27 megahertz. Let's go to 21. It's weird. It like doesn't change the way the sound is that much, going from 21 to 20. What was that? 27, I think. It's possible that based on the way the CPU is using the clock to generate the sound, that there are certain frequencies we can feed into it that will be accelerated, but the music won't sound out of tune. It just will change like the octave maybe that it's running at or something, because it doesn't seem like a direct relationship. It's not like going faster with the clock input just makes it go higher and higher and higher pitched. It kind of was going higher and then it would actually drop down again. So I don't quite get what's going on with that, unless there's some relation to the non-maskable interrupt that somehow affects it, or I'm not positive there. Right, how about Kirby's Adventure? We know that running this too slow seems to cause issues. How's it running? We're at 27.7 right now. So far so good. No issues. Okay, I just played through the first level here, and yeah, zero issues whatsoever, and that's running at this accelerated clock speed. I don't recall this game being laggy, like it's incredibly well optimized, so the additional overclock doesn't really do anything except for screw up the music. Okay, here's Mega Man 3. And of course, we have a little bit of a glitch there. That's due to the way this whole thing scrolled in. There's a Displaced Gamers episode on this, if I recall. But you see that little glitch that's happening there? That's obviously cycle counting gone wrong. Let's try one of these. Yeah, so that's par for the course with this kind of overclock. But any kind of slowdown that the game might experience, which I don't know where, because I don't play these Mega Man games that much. Oops. I don't know why I thought I could fire straight up. That is not a Mega Man thing. The parallax scrolling for the stars is working fine. All right, how about we go back to the EverDrive? Let's see if this works at this overclocked rate, because we did see some weird kind of glitching going on with it, at least at some of the speeds. Yep, definitely sparkly. Very interesting. This is a clone EverDrive. The real deal might work way better. And there we are, 2.34 megahertz for the clock speed, 148.6 cycles per scan line. In the last video, I tried to run this demo mapperless, and it wouldn't work. It's an unsupported version or hardware or something like that. Let's see if this can run now. Even though we're overclocked, it knows we're overclocked. So I'm going to put the frequency back to original speed, and let's see if this can run now. And then once it's running, yep, there we go. I can change this to like 28 megahertz, and let's see what happens. So I tricked the demo into working. So this doesn't use any mappers, therefore there's a lot of cycle counting going on, and of course that is going to be completely broken now based on the fact that we're overclocking the CPU, but let's see what kind of weirdness this does to it. So far, so good. Things seem okay. There was a little glitching on that initial kind of mapper comparison screen. But this effect works perfectly. Oh yeah, okay, I knew this wasn't gonna work here. Cycle counting gone wrong. Let's change this speed while it's running. Well, that crashed the game. That's me controlling the CPU clock speed, right? Okay, well, I think I've done enough fooling around. This was really just a proof of concept to show that this does work, and it totally does work. So I used a little arbitrary frequency generator device on a mod I did to a Commodore 16. I allowed it to switch clock speeds on the fly so I could run PAL or NTSC. And it was an Arduino, and it was controlling, essentially switching the kernel ROM out, so it was controlling the ROM address lines, and it was also programming the little frequency generator to generate the clocks I needed. So you could arbitrarily generate those on the fly, and I'm pretty sure that little arbitrary generator could go up to 30 megahertz without any issue. Therefore, it could easily be used on an NES to provide selectable or controllable overclock. So for instance, you could just use a little small Arduino with a little rotary encoder, and you could just alter the clock speed on the fly from stock and then just go up or down. The fact that the master clock and this clock input into the CPU don't need to be locked is kind of wild to me. In fact, I'm still a bit shocked about that, but you see the evidence here. I'm running Rico chips, and we're able to change the clock speed, and things seem to tolerate that 28 megahertz overclock without any issue. And in fact, Contra Force, which is one of the worst laggy games ever on the NES, is able to handle 30 megahertz, so 2.5 megahertz. It works perfectly. A lot of the other games freak out over 28 megahertz, but Contra Force does not. So if you want to try Contra Force on real hardware and you want to feel what it feels like to play that game without constant lag everywhere, the only way you're going to be able to do it is, yeah, crank it up to 30 megahertz and, well, the input into the CPU, that is, and then run that game. And then you can see for yourself what that feels like. It's just, you have to put up with the sound issues. So as I alluded to in the last video, if anyone ever comes up with a CPU replacement for the NES, they could, for instance, take the master clock in that's coming from the motherboard, use that for the audio portion, and then the CPU clock speed itself could be something you could arbitrarily control. that way you could overclock the CPU core without changing the audio side. And this is not real hardware. This would be an FPGA or a TNC or Raspberry Pi Pico, something like that. But should totally be possible. And wouldn't that be an amazing project to take an NES and overclock the CPU core selectively, and then with games that support like Contra Force, run it at like super speed, 3 megahertz or whatever, and as long as the PPU is able to communicate with that overclocked CPU and assume that it can handle 2.5 megahertz without any issue, then there you go, lag-free gaming, and then the audio can be not messed up as well. That's the key thing about using the software-defined CPU versus the actual hardware, which we're doing here. I think what I might do, just kind of for myself, is I think I have some of those frequency generators, a little board that I can control with an Arduino or any kind of microcontroller around. I think I'm gonna take one of those and try to like build it up into an actual console, and maybe have like a knob on the side where I can overclock it on demand. Yeah, that would be freaking cool. And maybe underclock it too if you really want to exaggerate the lag in a game. Then that's one way to do it, isn't it? So yeah, there we go. I hope you enjoyed this video. It was pointless again, but I don't know. I just love fooling around with this stuff, and I think it's pretty cool proof of concept to show that this really does work, and it's trivial to actually overclock your NES if you want to try for yourself. So if you like this video, thumbs up. If you didn't know exactly what to do, huge thanks to my supporters, subscribers. Subscribe if you haven't already, comment, all the usual YouTube stuff. And that's gonna be that. So stay healthy, stay safe, and I'll see you next time. Bye-bye.